All right. So last week we got a general prescription to go from the charge distribution. So that is rho and J, the charge and the current density, through the potentials phi and A, and then to the fields. So this week we are going to actually apply that for the simplest case, which is a single point charge, which is moving on some trajectory, okay, some arbitrary trajectory. So it has some path that it's following through space. It has a velocity, it has an acceleration, it has a position defined at every given time. So let's say you know those functions, how it is moving, and then let's actually try to find an expression for the electric field using the formalism we already developed last week, which is going from the going from the charge and current density to potentials and then to the fields. Now, before we completely delve into it, we need to discuss one important aspect, which we'll spend much of the week talking about, and that is retardation. Okay, and so the best way to picture that is with the equation we kind of ended last week. So this is an equation for the scalar potential given the charge density, right? And so this is the equation we derived. This was basically the solution to the Poisson equation, which phi has to satisfy. On the right hand side, the source term was rho basically, and this is the Green's function, 1 over r minus r prime. So this is a volume integral over the entire volume you're considering. R prime is the variable of integration, and r is the position at which you're evaluating phi. So, okay, so the argument of phi here, so it's phi of r, and r minus r prime, the absolute value is just the distance between the charge and and the place where you're calculating the potential, so the observer, so to say. Now this equation by itself tells you first of all, it's fine if the charge is just sitting there and it's not moving, but once the charge is moving, this equation is immediately problematic, because at least in this equation, the way it's written, it looks as though all the time coordinates are completely synchronized between the charge and the place where you're measuring the potential, right? So if I have a charge here at some time, and let's say I measure the potential because of the charge, you can see that there's no transformation on the time coordinate here. So the arguments of time here are the same as the arguments of time here. So both LHS and RHS have the same arguments of time, and that of course violates special relativity, because you can't have information traveling faster than the speed of light. So there must be a delay in the fields responding to the sources of the fields, and that information in vacuum is carried at the speed of light, and that delay is basically the distance divided by the speed of light. So everything that's happening here can only give you an effect over here with that delay, and that delay is called the retardation. And so these potentials, when you are explicitly putting the effect of the delay, are called the retarded potentials. And that's what we are going to calculate. So the notation I'm going to be using is I'm going to place anything that needs to be calculated at a retarded time in the brackets here. So for example, if I put rho in the bracket here, this is just an example equation. That means that you need to calculate rho at the retarded time. So that means that when you do the integration, or when you do any computation, the onus is upon you to make sure that you are obeying special relativity, that you're getting the correct amount of delay and coding the delay in. So let's see how we do that formally. So to do that formally, I'm going to consider a single point charge. Okay, so because it's a single point charge, I'm going to use a delta function along with rho to basically place the point charge at a given position in time and space. So I'm going to say that phi is basically a volume integral. That volume integral remains the same. And now to put in the effect of retardation, I'm going to put in integral over a dummy time variable t prime. So t prime is a dummy time variable. And then I have rho, which is the charge density, which I'm going to later replace with a point charge. But for now, it's the volumetric charge density at position r prime and t prime. And that's the Green's function that appears. And now I have a delta function here. So delta function of t prime minus t plus the distance divided by c. So this argument is quite interesting here, right? So this argument basically is making sure that we get the correct amount of retardation. That's what this argument is doing. And the way to see it, another way to see it is, let's say you integrate over dt prime, the dummy variable t prime, you're only going to pick out the value of this function when the argument of the delta function goes to 0, okay? And when does the argument of the delta function go to 0? It goes to 0 when t, the time at which you're calculating the potential, becomes equal to t prime plus r minus r prime by c. Okay, so when the time is equal to the time t prime, so you can think of it as t prime is the time of emission. By emission I mean the time at which whatever the charge is doing finally gives you an effect at the observer at time t. So that difference in time should be equal to the time it takes for light to travel from the charge to the observer. Okay, so that's what this delta function is doing. It's just a mathematical way to put in the retardation. And yeah, so that's the picture we have. The charge is at r prime, t prime, and then we are measuring the potential at r and t. And that integral here, by putting in an extra integral over dt, make sure that you have the effect of retardation baked in right now. Okay, so let's take a single point charge now. So I'm going to again replace rho now with another delta function. So that's the second delta function I'm talking about. And this delta function basically locates that single charge at a particular point in space. Okay, so Q is the charge itself. And then delta of r minus r naught of t. So I'm going to call r naught of t a function which I already know. So r naught of t is specified, and that is the trajectory of the particle. Okay, so r naught of t is basically the position vector of the particle as a function of time. And yeah, if I take the derivative of this with respect to time, I get the velocity. I take the second derivative, I get the acceleration. Okay, so that's what r naught is. That's the trajectory of the charge, and that's already known. And notice that delta function has units of 1 over the units of its argument. So this is a three-dimensional argument. So there are 3 spatial coordinates. So this has units of 1 over centimeter cube, right? The same as the charge density. So charge times 1 over centimeter cube gives you the charge density. Okay, so that's what we're doing. So now we have 2 delta functions, right? So we have one delta function for the retardation. We have one basically to locate the charge. And so now the 3-dimensional integral over the volume is trivial. So you can just carry out this integral. That integral is basically the value of the integrand at the position where the argument of the delta function goes to 0. So basically we have to replace, whenever you see r prime, you replace that with r naught, right? That's what this integral would do. So now we are left with one time integral. Okay, so the potential at r and t is equal to a single integration over t prime. So one of the delta functions is gone, and we got rid of it by replacing all of the r primes by r naught. Okay, so one notational simplicity, because the algebra is going to become very cumbersome in this derivation, is I'm going to call capital R of t prime as basically the vector that goes from the place where you're measuring the potentials to the place where the charge is. Okay, so the charge at time t prime. Okay, so again, don't lose sight of the different coordinates here. I'm measuring phi at time t, but I'm doing an integral over coordinates t prime. Okay, so t prime is the variable of integration here. So when you finally do the integral, t primes will disappear and you'll only be left with t, which is the t is the time at which you actually want to calculate the potential. Okay, so with that notational simplification, you get a fairly simple equation. You have an integral over t prime of the delta function that takes care of retardation. This is the charge, and this is 1 over r. Okay, I mean, we could have basically started off with this equation. We could have just written this equation as is. by noting that the potential of a charge is just 1 over the, is just q divided by the distance to the charge. So q divided by r is basically the, the potential, the scalar potential. But we have this, we have this mathematical trick of putting an integral over a dummy time coordinate with this delta function to make sure that we get the correct retarded value for the potential. Okay, so we don't violate special relativity. And so now everything comes down to, how do you evaluate this integral? You already know how to evaluate integrals with delta functions. So if I give you, integral over some variable and a function, and then multiplied by a delta function, yeah, that integral just returns the value of the function at a point where the argument of the delta function goes to 0. Now, in this case, it's a little more complicated because the variable of integration is t prime, but inside the delta function, you have r of t prime. So you have a function of t prime. So things are a little more complicated when you have to do that. You can't just equate this to 0. There is a Jacobian involved because you have a function inside. If we just had t prime minus t, things were simple, right? That's the standard delta function integration you've seen. But now we have a function of t prime. So you need to be a little more careful in getting the right Jacobians when you do the integral. So let's do that. So this is what I just mentioned. So if you have a function g of x times delta of x minus alpha dx, that's g of alpha, right? That's the definition of delta function. But that's a very specific form where you only have x here. But more generally, if you have g of x delta of f of x minus alpha, so instead of just x, I have f of x. Then that's what the integral gives you. It gives you g of x divided by the derivative df by dx evaluated at x equal to alpha. Well, of course, if you put f of x equal to alpha, df by dx is 1, you get g of alpha. It works out. But if you have x, which is a higher order function or a more rapidly varying function, if f of x is, let's say, x square or x cube or something that is more rapidly varying, then you can kind of intuitively see that this integral is going to be smaller and smaller, because even a small change in x is going to create a large change in the argument here. So when you actually take the Jacobian into account, that delta function as a function of x becomes narrower and narrower, because you have to change x by a very small amount for f of x to change by a large amount. And so this is what the derivative is doing. So that derivative is just normalizing for the value of, instead of just saying g of alpha, you're going to reduce the value by df by dx, which is just a measure of how quickly the argument of the delta function is changing as a function of x. Right? So we can just put that through. So in this case, we have g of t is the integrand we have. So that's just q by r. Q is the charge and r is the is what was in the denominator. That just comes from the Green's function. And f of t prime, which is actually what goes inside the delta function, if we go back, is basically instead of just having t prime, you're having t prime plus r of t prime by c, right? So that's basically t plus r of t prime by c. And now we need to say, okay, what's the derivative of that? Well, that's easy. So the derivative of t prime is just 1. And then now we need a derivative of r of t prime. So what's the derivative of r of t prime? So notice that r is basically the distance between the charge and the observer. And you're asking what is the speed at which, that distance is changing. That's just the velocity of the charge projected along the line joining the observer and the charge, right? So if the charge is moving perpendicular to the line of sight from the observer to the charge, then r is not changing. There's r only changes if the charge has a velocity which has a component along the line of sight from the charge to the observer. So r of, the time derivative of r, which is the velocity of the charge, beta. So I'm going to define beta as v by c. So v is the velocity of the charge, times the unit vector, right? So this is a dot product. So it's just taking the component of the velocity along the line joining the observer and the charge. And that's the rate at which the distance between the observer and the charge changes. So, I mean, this is just a statement of the time derivative of distance is velocity. It's just that in this case, we have to take a projection of the velocity along some axis because the tangential velocity does not contribute to a change in distance. Okay, so that's it. So we have the potential now. We're basically done. So you get Q divided by R of 1 minus N, which is the unit vector connecting the charge and the observer, times beta, that's the velocity of the charge. And that's basically this expression here. So I've just put in df by dx, and you evaluate it at x equal to alpha. And so that's what this is. So phi is just q divided by r, and that the df by dx, that's the Jacobian, is this factor 1 minus n dot beta, and you evaluate it at x equal to alpha, which in this case is that retarded time. So you have to evaluate this expression at a time t prime such that this condition is satisfied, t equal to t prime plus r of t prime by c. Okay. So what's happened here? So in the static case, we just had q by r. We now have this extra expression once you put in the effects of retardation. And this, you can think of this as just the Jacobian. This is again a scaling factor. This is just a Jacobian. And notice that if B is very small, if the charge is not relativistic, remember B is, V by C. So beta, if beta is very small, then this factor is basically 1. And then you get back your non-relativistic kind of a static result, which you had. We can do the same for the vector potential. Again, the vector potential is satisfies also a Laplace equation, just like the scalar potential did, but instead of the charge, we had current density. And so, the same procedure can be followed. You can kind of expect that in the numerator, you're going to end up with some velocity because the current density is equal to charge times the velocity. So you'll end up with a factor beta here in the numerator. And the rest of it remains the same. You have 1 over r and you have this Jacobian. So this factor, I'm going to often call this as kappa. And remember that kappa is just equal to 1 if things are non-relativistic. But kappa is generally, the Jacobian, which you get when you integrate over the dummy variable dt prime. And so here's the compact notation. The potential at position r and t is equal to q multiplied by 1 over r. R is the distance between the particle and the position at which you're calculating the potential, times kappa, which is the Jacobian I just spoke about. And all of this has to be evaluated at the retarded time. Okay, the retarded time is equal to t prime such that this equation is satisfied. And that just takes care of special relativity, right? It just takes care of the fact that information travels at the speed of light in vacuum. Again, for the current the vector potential, is just similar to the scalar potential, but you have a velocity term that gives you a beta in the numerator. Again, all of that evaluated at the retarded time. So these are basically called the retarded potentials. So these are the potentials of an arbitrary moving charge. Okay, so you can put in any prescription you want for the trajectory of the charge, and you can ask yourself at an arbitrary location in space, what are the scalar and vector potentials of a charge? And they can kind of be written in this compact notation. I mean, the notation is compact, but all the complication comes in you actually getting the retarded times right? So we can't give a general solution for the retarded time because it all depends on what the trajectory of the particle is, right? I mean, there's no general solution for the retarded time other than just this equation. So for every specific case, if I tell you the particle is going in a straight line, it's going in a circle, once I tell you what the trajectory is, you can basically plug that trajectory into this r over here. And remember, r is just the r is basically just the distance between the observer and the particle at time t prime, and then solve this equation to get the value of t prime and plug that t prime in here and then calculate the potentials. Yeah, so far simple. Everything is similar to the static case, but for this kappa and but for the effect of this retardation. Now the next point here is now to go from the potentials, which is phi and A, to the electric and the magnetic fields. And I'm going to go through the derivation there. But I just want to warn you that the algebra becomes kind of complicated. So I won't expect you to actually be able to, very easily derive all of the algebra, go through all the algebra. I mean, I tried to go through this myself and it took me, hours to actually get everything right and to get the final expression right. So I want you to go through the algebra once, at least in these videos, so you kind of appreciate what goes behind the works. But if you can't like freely derive it yourself in one shot, then don't worry about it. I mean, like I said, it took me hours to get all the algebra right. Okay, like I said, going from phi to A to E to B is going to be cumbersome. I mean, what do we need to do, right? We really have to take, if you remember the equation, to go from the potentials to the fields, if you take the electric field, it was the gradient of phi, there was a time derivative of A. So we are basically doing spatial and time derivatives of phi and A, right? So let's look at what they work out to be. So let's say we want to do the gradient of phi. So it's a spatial derivative. Gradient of phi is a vector. And if you go back and you say, okay, where does the gradient apply? You're basically applying the gradient on, this R here, this kappa here. This is what the gradient is really working on. And basically the gradient is working on R, right? I mean, that's the only spatial quantity there. Actually, sorry, I need to go back. The gradient only works on R, right? There's no spatial coordinate in kappa. Kappa is just, actually the gradient will work on N because that is a spatial coordinate. That's a velocity coordinate. So it's basically going to work on R and N. And again, N is just a unit vector along R, right? That's what N is. N is the unit vector along the line joining the observer and the charge. So basically you need to just calculate the gradient along R. So once you know how to take the gradient along R, you're done, right? So that gradient operator, because that gradient operator is only to be calculated along R, because in a plane perpendicular to R, there is no gradient. The gradient is always going to be 0 because there is no term here which gives you some spatial coordinate perpendicular to that vector R. Okay, so everything depends only on one of those axes, which is going along R. So another way to think about this is a gradient is a 3D operator, but if you choose one of the axes, your x, y, z, if you choose one of the axes to lie along R, then only the d by dx term is going to be non-zero, right? Because there's no other variation along the y and z axis. So basically what I'm saying is, choose one of the axes of the coordinate system to be along R, then the gradient just becomes a differentiation with R. That's the partial derivative with R. That's all I'm saying. Okay, so let's see. It turns out that it's very hard to take a differential of this expression here. It's actually much easier to take a differential of this equation here. Okay, so I know how to take a spatial derivative of that. So if I try to take a spatial derivative with respect to R, I can push the derivative inside the integral, and I know how to differentiate these kind of quantities. Whereas I don't really know how to differentiate some quantity evaluated at some retarded time. That's just notationally difficult. So let's go back to that equation here, and I'm going to take the gradient. And now, so the gradient is, just going to lie along N, which is a unit vector along R. That's the line joining the observer and the charge. And now I'm going to have to take a partial derivative with R. And so there are two terms here, the delta function and 1 over R. So I'm going to use the product rule. So one term of that will be the delta function as it remains. And the derivative of 1 over R is minus 1 over R square. And the second term in the product rule is 1 over R, and it remains as is, and the derivative of the delta function. And so the derivative of the delta function, again, you have to use a chain rule here. That becomes delta prime. So prime denotes derivative with respect to the argument. And then the derivative of the argument itself, which is 1 over C. right? So the derivative of the argument itself is just 1 over c, because r over c is the term here. Okay, so that's what the potential looks like, the gradient of the scalar potential. Now the other term which is going to enter the electric field is dA by dt, right? Because the electric field was minus of gradient of phi minus 1 over c dA by dt. And so let's do the time derivative now. So instead of the spatial derivative, we are going to take the time derivative, but this time of the scalar, of the vector potential. Okay. Okay, so let's do the time derivative. So if you take the time derivative, then you're basically the only quantity that explicitly depends on time is basically the delta function, which is inside the which is inside the integrand. And so the time derivative is just going to be delta prime, and then use the chain rule, and the time derivative of this is 1, minus 1 in fact, and so you get a minus sign outside there because you have a minus t here. Yeah, so that's basically the time derivative of A. I mean, notice here that we are taking derivatives with respect to certain quantities. Okay, so in this case, I'm taking derivative with respect to t, which is the time at which the potential is measured. And so you're going to have to take, these are partial derivatives, right? These are not full derivatives. And so when you take the partial derivatives, you shouldn't differentiate with respect to t prime here. Even though t prime and t are connected, we are doing partial derivatives here. So you only take a derivative with terms which have the actual t in them. Okay, so even though if I change t, then t prime and r also have to change to make sure that the retarded time is calculated properly. But I'm taking derivative with respect to t here, not with respect to t prime or r. Okay, so you put all of that together. E is minus gradient of phi minus 1 by c dA by dt. So I've done this here. You can always pause this video and then go through the derivation yourself and check the terms. I've basically added these two together, and then there's a 1 by c here, and then you get the electric field. And how do the integrals end up being evaluated? Let's go through it term by term. So the first integral here is an integral which you already saw. So it was basically an integral of something with this delta function inside it. And then, we knew how to do it. It basically ended up being the value of the integrand here. So whatever is outside the delta function, but there was a kappa factor in the denominator, right? So that was basically the derivative of r with respect to time. Yeah, so the first term is basically very similar. So you have n hat, the unit vector, divided by r square. There's a kappa there, but of course you have to do all of that at the retarded time. Okay, so here's the second term. The second term is a little more complicated because you don't have a delta function. You basically have delta prime, which is a derivative of a delta function. So in this case, it's derivative with respect to this argument. And again, I'm going to spare the details here and just go to the final expression. But I just want to tell you how to do these integrals. So if you have so if you remember, you have a function times a delta function, and you do an integral, you just get the value of the function at some point. That point being the point where the argument of the delta function goes to 0. Now it's very similar if you have a derivative of the delta function. So instead of just getting the value of the function itself, at some point you get the value of its derivative at that point. Okay, so this is going to evaluate to the value of the derivative of beta minus n hat divided by CR. So instead of just its value, it's going to be its time derivative. Actually, it's going to evaluate into the derivative, not just with respect to t prime, but derivative with respect to t prime minus t plus r by c, because that's the argument of the delta function. But again, you can get rid of all of that with the Jacobians, right? The Jacobian is just kappa, but in this case, there are going to be two Jacobian factors. So one is going to come from the integration, from the fact that the argument here is not exactly just t prime, but a function of t prime. The other kappa is going to come from the fact that you need to take the derivative of this function with respect to t prime minus t plus r by c. But we want to write it as just a derivative with respect to t prime. So there's a chain rule and another factor of kappa that comes in. So that's the second term here. So we have 1 over kappa. There's another factor of kappa. So there are 2 kappas in this case. Here there was only 1. And now we need to take a time derivative of this and evaluate that time derivative at the retarded time. Okay, so things are getting more complicated. But anyway, so we can, it looks very complex algebraically, but if you really sit without too many distractions and then go through the steps carefully, you do get to the right answer, like I did here. Okay, so how do you get this derivative now? So once we get the derivative, we're basically done. I mean, just notice the factors which are there in this derivative, right? So you need to take a derivative of n, beta, kappa, and r with respect to time. So how do you do those derivatives? Well, again, you need to keep applying chain rules to be doing that. And in the end, it'll turn out that you only need to evaluate 2 derivatives, so dn hat by dt prime, and you need, of course, d beta by dt prime. I mean, this is just the acceleration, right? So this is just beta dot. That's just the acceleration. Dn hat by dt prime is a little more involved. This is basically telling you what is the time rate of change of the unit vector, which is connecting the observer and the charge. And the time rate of change of the unit vector is just the perpendicular velocity divided by r, right? So that is going to be the time rate of change of the unit vector. Because if you have any parallel component of the velocity, it doesn't change the unit vector. You need to move perpendicular to the line connecting the charge and the place where you're measuring the potential to actually change the unit vector. And so it's basically just the perpendicular velocity by r. And so the question is, how do you write an expression for the perpendicular velocity? And here is one way to get the perpendicular velocity. You just take, n hat cross beta. So you can, have a look at why this is the perpendicular velocity. This basically, just apply the cross product rule, and then you can kind of see why this is the perpendicular velocity. The parallel velocity was n hat dot beta. And so if you want the perpendicular velocity, then, you just need some cross products to get that value. And yeah, divided by r. Okay, so that's dn hat by dt. So we have an n hat here, we have a beta here, we know how to differentiate that. Kappa, again, just has beta and n hat in it. So kappa is 1 minus n hat dot beta. So if you know how to differentiate with respect to n hat and beta, you know how to differentiate with respect to kappa. You know how to differentiate with respect to r. R is just the distance between the charge and the observer, and so the time derivative of that is just going to be the line of sight velocity. So it's going to end up being something like beta dot n hat. Right, so that's the velocity along the line of sight. So once you know how to differentiate each one of these terms, you just keep applying the product rule and you can get all the derivatives. Again, I'm going to spare the details here. I just have some intermediate steps here for people to check their answer to make sure that they're on the right path. But I'm just going to give the final expression here. So here's the electric field. So it turns out that you can write the final expression in 2 parts. So one part has an r square in the denominator, the other part has an r in the denominator, and the part with r square, notice that it does not depend on the acceleration. So there's no beta dot here. So they're just velocities, betas here. The one that depends on r has beta dot. So there is an acceleration term over there. So what does it mean? If you're really far away from the charge, then this term is going to be subdominant, right? This term is going to be very small. This term is going to be much larger because it's just 1 over r, not 1 over r square. So very far away from the charge, this is the term which you're going to see. Okay, and that term depends on the acceleration, not just the velocity. If you're very close to the charge, then this is the term which is going to be dominant, and it doesn't depend on acceleration. It just depends on the velocity. And the electric field going as 1 over r square is the Coulomb field, right? So the Coulomb potential goes as 1 over r. The Coulomb electric field goes as 1 over r square. So this is called the Coulomb term. So this is the term you get just from, the fact that the Coulomb potential of a charge goes as 1 over r square. Now, this term is there regardless of whether the charge is accelerating or not. Whether beta dot is 0 or some value, it doesn't really matter. So you always have the Coulomb field of a charge. That's always present around the charge. Now, this term is really interesting because it goes to 0 if beta dot is 0. So this term only exists if the charge is accelerating. If it's going with uniform velocity, this term does not exist, right? So this is called the radiation term. And it's called the radiation term because it goes as 1 over r. And you'll soon see that it gives rise to a Poynting flux. And it gives basically rise to energy which is being radiated away. Because when you actually do the E cross B, you actually get a Poynting flux from this term. So it's called the radiation term. This is the term that dominates at large distances. And notice that this term requires you to have an acceleration. And so that is why we say that accelerated charges radiate energy. So we'll actually calculate the Poynting flux soon. And this is where that idea comes from, that accelerated charges radiate electromagnetic energy. And the converse is also true. To radiate electromagnetic energy, you need accelerating charges. If you don't accelerate charges, then you just end up with this Coulomb term, and it doesn't give rise to a radiation field that can travel large distances. Again, you can go through all of those steps again for B. So B is, there's no gradient of phi in B. It is just curl of A. So again, you need to take the curl of A. It turns out that B is just going to be n hat cross E. Okay, I mean that kind of makes intuitive sense, because if you have some radiating field, then E and B are basically perpendicular to one another and perpendicular to the direction of propagation. So in this case, n hat is going to be the direction of propagation. And again, the magnitude of B and magnitude of E are the same in Gaussian units, right? So this expression totally makes sense just from the intuition we had from previous week from the solution to plane waves. Special case if beta far less than 1, so charges are not relativistic. So 1 minus n hat times beta is kappa, which is just going to be 1, almost equal to 1. And the other terms, you can just set beta equal to 0. And so you get the value for the electric field. You again have the static field, which is the usual form. It's 1 over r square. This is just basically the Coulomb solution, right, to the electric field of a charge. Plus, now you have this term depending on acceleration, but of course it has a much simpler form for a non-relativistic charge, and that's called the radiation field. Of course, all of this has to be computed at the correct retarded time, which, there's no general solution for it. It depends on the trajectory of the particle, how you get the correct retarded time. So that's the formula for the electric field of an accelerating charge. Now, I mean, it is true that this equation is kind of complicated. There are just too many terms, cross products, dot products inside kappa and unit vectors, the retardation and all of that. So it's kind of unfortunate that even the simplest of simple cases where you have a single point charge which is accelerating, the electric field turns out to be such a complicated expression. But it's also fortunate in that, it is amazing and beautiful that you can just write this down on a sheet of paper, and it's true and it works. So, in some sense, it's also simple in that something as complex and beautiful as electromagnetic radiation, the basic equation from which you can get everything else can just be written down on a sheet of paper. So, it's a nice thing, but it's also an unfortunate thing that, sometimes when you actually apply this to different cases, things get pretty complicated algebraically very quickly. It turns out that this expression is not that complicated algebraically. It's much easier to use. So to gain some intuition, we're going to solve some problems where the charges are not relativistic. So you can actually assume beta far less than 1 and actually calculate the electric field. It's better to build intuition so you don't get completely lost in the algebra of evaluating this hideous expression here. The other utility is, you can always, we're going to do frame transformations with Maxwell's equations later, I believe next week. And, you can always transform to a frame where, the charge, you can transform to the rest frame of the charge, right? And then if the charge is not moving relativistically. And then you can always calculate the fields in the rest frame of the charge and then use the Lorentz transformation for the electric and magnetic fields to actually get the fields in the lab frame or in the observer frame. So anyway, so we're going to work with this. We'll do a few examples of application of this expression to get some intuition. But yeah, in a nutshell, this slide here tells you the electric and the magnetic fields of an accelerating charge.